This is 2.3 Alkanes. So in this topic there are quite a few points, but it's actually not a terribly long topic. So you need to recall that alkanes are described as saturated hydrocarbons. Explain in terms of van der Waals forces the variation in boiling points between the alkanes with different numbers of carbon atoms. Explain in terms of van der Waals the variation in boiling points between structural isomers of an alkane with the same molecular formula. Describe the complete and incomplete combustion of alkanes in air and link the appearance of the flame to the amount of carbon present. Recall that pollutants such as carbon monoxide, carbon, oxides of nitrogen and sulfur and unburned hydrocarbons are produced during the combustion of alkane fuels. Recall that the percentage of carbon dioxide in the atmosphere has risen from 0.03 to 0.04 because of combustion of organic compounds and is believed to have caused global warming. Explain how a catalytic converter reduces the environmental impact of burning alkane fuels. Describe the substitution reactions of alkanes by chlorine and by bromine. Then define the terms radical, homolytic and heterolytic fission, and finally outline the radical substitution mechanism involved in the photochemical halogenation of alkanes in terms of initiation, propagation and termination steps. So, alkanes are the simplest type of organic compound. They are saturated hydrocarbons and contain no carbon double bonds or triple bonds. We know that organic compounds are named according to the IUPAC system of nomenclature. The name is composed of two parts. The first part, or prefix, indicates the number of carbon atoms in the longest unbranched carbon chain. The last part, the suffix, indicates which functional group is present. So with alkanes, the last part of the name ends in ANE. And the names of the first 6 unbranched alkanes are shown below in this table. So 1 carbon is meth, 2 is eth, 3 is prop, 4 is bute, 5 is pent, and 6 is hex. And we can see that we have then methane, ethane, propane, butane, pentane, and hexane. And when you look at each formula, each one increases by 1 carbon and 2 hydrogens as you go down the group. So as carbon to hydrogen bonds are considered to be non-polar, the only forces acting between alkane molecules are van der Waals forces, and these increase, as we know, in strength as the relative molecular mass of the molecule increases as there are more electrons present. So consequently, the boiling points of the alkanes increase with increasing relative molecular mass. However, with increasing branching in isomeric alkanes, the boiling points decrease as the molecules can't get as close, and so the van der Waals are not as strong. For example, the boiling point of 2-methylpropane is minus 11.7 degrees, and it's lower than butane, which is 1, despite both molecules having the same molecular mass. When we look at reactivity of alkanes, first we look at combustion. So they're generally unreactive, although they do undergo complete combustion, producing carbon dioxide and water. They're characterised by having large enthalpies of combustion and are used as fuels because of this. And we see here the example of methane reacting with oxygen to give us carbon dioxide and water. You need to be able to balance equations for complete combustion of the alkanes. The flame is orange and becomes a more sooty flame as the carbon content increases. So incomplete combustion then leads to the formation of carbon monoxide, which is odourless, colourless and poisonous. And a sooty flame shows incomplete combustion. So when alkane fuels combust, the following pollutants occur. Carbon dioxide, carbon monoxide, we get carbon, we also get sulfur dioxide because of sulfur impurities, we get oxides of nitrogen because the high temperatures, particularly in internal combustion engines, allow oxides of nitrogen to form, and we also have unburned hydrocarbons. So these pollutants are responsible for a number of environmental problems, such as acid rain, global warming and smog. The percentage of carbon dioxide in the atmosphere has risen from 0.03 to 0.04 due to the increased combustion of organic compounds, and that's believed to have caused global warming. Catalytic converters in an exhaust system reduce the environmental impact of these pollutants by converting them to less harmful products. And there's a picture of a catalytic converter there. Substitution reactions then are where one atom or group is replaced with a different atom or group. Alkanes can react with halogens such as chlorine to produce halogenoalkanes in a substitution reaction. We see here methane reacting with chlorine to give us chloromethane, and the other product then is HCl. So in the initiation step, ultraviolet light is required to produce things called radicals. So a radical is a particle with an unpaired electron. The radicals are formed via homolytic fission, and this is bond breaking in which one of the shared electrons goes to each atom. And the highly reactive radicals react with the alkane molecules in a sequence of propagation steps, producing alkyl radicals with more halogen radicals. The reaction is completed when the radicals react to form more stable species, and that's called the termination step. You see here in the initiation step we have chlorine with UV light giving us these two chlorine radicals, and those radicals are represented with this dot. In the propagation step, it's the radical reacting with an alkane to give us an alkyl radical, and then that radical further reacting with chlorine here to give us more chlorine radicals. You see in the termination step that involves anything where there are two radicals joining together. So in this case, two chlorine radicals giving us chlorine gas. Here we have a methyl radical and a chlorine radical giving us chloromethane.